What's up, ladies and gents? This is Mr. Cloud coming from North Belmore, New York here. Yeah, that's right, geologists are nice, tough, and a little bit wacky. Oh yeah, a little bit of a geology joke to start us off today. We're about to get into an awesome discussion, an awesome lesson on metamorphic rocks. The third screencast in our series of screencasts on rocks and minerals. Let's get going tonight. Here we go. Metamorphic rocks, guys, here it is. All right, our last type of rocks. We have two different photographs here from our favorite park in the world, Central Park. So just wondering, if you've ever been to Central Park, you might have walked on these massive boulders and maybe you had no idea what they were. Maybe you just didn't care whatsoever. Well, if you're a geologist, you definitely do care. And these are actually massive boulders, what we love to call Manhattan schist. Um, the striations and parallel grooves you see here are really recent. They're made when glaciers pluck rock and then drag that rock over top, and they give you the appearance you see today. But the rock itself, I'm worried about in this conversation. I'm worried about, not worried, but interested in the rock itself. And this is schist, which is a metamorphic rock. So what I want to do today is talk to you about what causes rocks to change. Okay, think about how a butterfly is created, right? It's kind of a larva. It's like a little, I don't know, caterpillar type thing. It chows down a whole bunch of food. It gets bigger. Then it turns into a beautiful, wild-looking pupa, and then goes through a whole process of metamorphosis into a beautiful butterfly. Okay, or think of a frog, right? It's an egg and then a tadpole, then it loses its tail and then it becomes a frog. It goes through metamorphosis as well. Metamorphic rocks change. They go from one type to another. And what I wanted to do is break down that process and talk to you about that specifically today. Okay? So, our good friends here in Central Park enjoying the Manhattan schist there, that has been there since the Cretaceous period. Wow. Well, over 100 million years at least ago. Right? Metamorphism, what is it specifically? It's the changes that occur in solid rock due to great temperature, great pressure, and chemical activity. So our three main, factors of change are: 1, heat; 2, pressure; 3, chemical activity. In earth science class, we focus mostly on heat and pressure, but you're really not going to have a lot of metamorphism happening without the chemical activity of water. That does a great job transporting minerals and really changing the melting temperatures down there within Earth's interior and really driving the change that's going on here. Okay? Before we get into any of those processes, though, let's get into some terminology that you need to know with metamorphic rocks. Okay? And that is this conversation here. The good old protolith conversation, folks. Protolith. Protolith, guys, in layman's terms, it's the parent. It's the parent rock. All right? So all metamorphic rocks can come from particular rocks, but they always come from something else. We call those rocks parent rocks. They're the pre-existing rock from which a metamorphic rock is formed. Parent rocks become daughter rocks. For example, limestone becomes marble. Limestone's the parent of marble. Sandstone becomes quartzite. Sandstone is the parent or protolith to quartzite. And hornfels has got a whole bunch of random rocks that it can become hornfels. Gneiss is the same way. It can be a lot of other parent rocks that becomes gneiss. But specifically, guys, is when one rock becomes another. Okay? Got to know that terminology. All right? So let's get into the different types of metamorphism. Right? There are two main types of metamorphism. There's contact metamorphism and regional metamorphism. We're going to break these down. The first one we're going to talk about is the most common form of metamorphism. Can you guess what it is? Well, this produces by far the most amount of metamorphic rock. It is regional metamorphism, so let's get into that here. You see this massive block diagram here? Well, we can see the Earth's interior, and we can see the movement of Earth's plates. On this side over here, you clearly see the oceanic crust moving towards the continental crust. A collision happens, and we get subduction. And this is happening over a very, very large region. So when rock dips down and there's a tremendous amount of pressure on the parent rock, those protoliths there, they're going to start to metamorphose. And they do this in a regional fashion. Okay? So regional metamorphism occurs over large areas and is associated with mountain building. You get deeply buried igneous and sedimentary rocks that are squeezed by the weight of the rock layers above. But it's not just igneous and sedimentary. You can have metamorphic rocks becoming other metamorphic rocks too. Okay? In the process that we see here, from slate to phyllite to schist to gneiss. Okay? Here's another block diagram to kind of show you convergence, and really this is commonly how regional metamorphic rocks are built. These areas are going to experience massive amounts of heat and pressure. What we see here, let's move my face around a little bit so hopefully you can see it a little bit better. You start to see how regional foliated rocks go from low grade and eventually to high grade metamorphic rocks. Okay? As you go from the upper left, which is a sedimentary rock formed by diagenesis, it'll slowly heat up, get more and more pressure that starts to build. You get layering, you get foliation happening. Okay? In slate, what you get is this mineral alignment happening that is very, very fine in texture. And then you get slate can become phyllite, or phyllite, any way you want to say it. And then phyllite becomes schist, and you get these larger crystals that start to grow. Phyllite and schist are very hard to tell the difference unless you're a geologist, but phyllite really has microscopic microcrystals that you can't see with the naked eye, whereas schist has larger crystals. And then schist can become gneiss, and gneiss gives you these zebra stripes, the banding pattern that you see here. Okay? We go from low to high grade metamorphism, and this is happening with regional metamorphic rocks. Let's take a pause for a second. What I recommend that we all do is take out the Earth Science reference tables and turn to page number 7. Let's do that right now. All right, guys, we're back. So here's page 7 of the reference tables. I hope you all had the opportunity to break them out and open them up. And what I want to do is just kind of focus in on the regional metamorphic rocks here for a moment. I'm going to use my highlighter tool here, and maybe we'll use blue. Okay, so on page 7, you're going to see, guys, that metamorphic rock identification scheme is separated into two really different zones. The first, guys, is going to be your foliated rocks over here, and that's what we're talking about right now. For the most part, regional metamorphic rocks are foliated. Okay, and on your chart, you only have 1, 2, 3, 4 choices to choose from fine to medium to coarse grain. Okay, so the first thing you're going to do whenever you're identifying metamorphic rocks is you're going to check it out. Is it foliated or is it non-foliated? And then you're going to go from there. You're going to figure out grain size. You're really going to go down to comments right there. I just wanted to make sure that we realize that this conversation of low grade to high grade metamorphism happens right here on the reference tables. Okay, and it shows you here heat and pressure increases as you go from slate to gneiss. All right, let's go back, guys, to what we were talking about before, and we're going to shoot right on back here and continue with our conversation. Okay, so we talked about regional metamorphism. The next type is contact metamorphism. Okay, and with that, guys, this really occurs when molten rock comes in contact with surrounding rocks, and you get all these different types of rocks that form. So let's really get into that a little bit more clearly. And I'm going to pull up, guys, a diagram for you. Okay, here you go. Hopefully everyone can see that pretty well. Slide myself over. Again, I'm going to use my editing tool, and I'm going to talk to you guys a little bit about how contact metamorphism works. Okay, so I'm going to do this freehand. Hopefully it works out pretty well. I'll use the color red, and I want to show you what happens here. So really, guys, what you're going to see is you're going to see, let's see here. You're going to see, okay, an igneous intrusion kind of moving in to an area of pre-existing rock. Here's my igneous intrusion. Okay, so I'm going to create a little text area down over here. I'm going to type that in. Okay, this is an igneous intrusion. Okay, and really what it is, guys, is this is just magma. Okay, all right, it's liquid red hot magma moving upwards. Okay, going up. All right, this way. Okay, so you can imagine how hot this rock is, guys. It's super hot. And when that happens, guys, it starts to slowly change the rock that surrounds the intrusion. Okay? And in earth science, what we do is we actually use kind of a hatchet symbol to show that. Okay? Kind of like those hatchet lines in topographic maps, completely different meaning, but it kind of looks the same. And this is showing us that contact metamorphism is happening around this igneous intrusion. Okay, so you can be asked common questions that you might have to come across. What I mean by that, okay, is I want to highlight some of the protoliths here, or the parent rocks, and I want us to figure out what rocks they will become when they're contact metamorphosed. So let's first start talking about this one. All right, the red wall limestone here. Okay, so this is limestone. That's the parent rock. And as you can see over here, it's being contact metamorphosed. So what I want you to do is use page 7 of the reference tables. I'm going to pause, you're going to pause, and let's try to figure out what limestone will become. All right, guys, did you figure it out? Well, limestone, guys, when exposed to contact metamorphism, is going to become marble. There you go. That's what it's going to be. Hopefully you were able to figure that out. Okay, let's do another one together. All right, so let me use the highlighter tool again. All right, and we'll use a more colorful color. Let's go down over here to the sandstone. All right, this is a really common question. So this sandstone is being contact metamorphosed. What do you think it might become? Pause the video and let's try to figure it out. All right, sandstone will become what rock? All right, guys, here we go. Let's do it together. Pause the video now. All right, guys, did you figure it out? I hope that you did. All right, well, let's check it out. Let's see what it's going to be. All right. Well, that kind of disappeared on me, didn't it? All right. Well, the sandstone layer down here should become quartzite. Okay. So hopefully that was helpful for you. In figuring out what a metamorphic rock could potentially be. Okay. So now let's get out of this here, and we're going to go right back to the video. All right. Hopefully that spiel was beneficial for you to figure out how contact metamorphism creates metamorphic rocks. So now, how do metamorphic rocks actually change? Right? So they change in two different ways. Okay? They change by crystalline texture and by density. So let's break that down together. Okay? So we have all this heat, all this pressure affecting the rocks, right? And there's a term that is only used with metamorphic rocks. And that term, guys, is the term recrystallization. Repeat it to me, recrystallization. Okay, what does that mean? So under heat and pressure, the size, shape, and spacing of grains will change. Rocks may partially melt and fuse together, forming larger crystals, or pressure may break the grains into smaller pieces, destroying the original texture of the rock. We call this recrystallization. So here's an example of sandstone. When, let's say, it gets contact metamorphosed, the sand grains will kind of fuse together. They'll become more dense, and you'll get quartzite. Okay, we call this recrystallization of the rock. Now, you can imagine, guys, you remember from one of the first lessons in earth science, guys, if you put something under greater pressure, does that change density? Of course it does. Because as pressure goes up, volume goes down, density goes up. So it's your second would be increased density. So pressure from deep burial closes pore spaces in sedimentary rocks and openings in igneous rocks. So if you had some sort of vesicular rock that was buried ridiculously deep down, you're no longer going to have those spaces anymore. All right, they're going to be closed down, and you can see an increased density for sure. Okay, so the mass is forced into a smaller volume, causing density to increase. Right? So now let's talk about visual characteristics of metamorphic rocks and what can you actually see. Well, the first is going to be foliation. Foliation is a fancy term for layering. It results when mineral grains recrystallize and are flattened under pressure. Okay, so rocks are said to be foliated when its crystals are arranged in layers of bands, along with the rocks breaks easily. There are two types of foliation, one being mineral alignment, which doesn't show any really differences in colors there. And the second type of foliation is banding. And this occurs when minerals of different densities recrystallize under pressure and separate into layers, kind of like oil and water. Okay, here's banding. This is clearly nice right here. And in our science class, I love to call these zebra stripes, because if you see those zebra stripes, it's clearly nice. Guys, it's nice when it's nice zebra stripes. Okay. Also, This gives you this kind of wavy look, which is kind of distortion, because you can get like differential pressure that's happening, causing the waviness of the distortion, all right, that you clearly see, all right, with these nice outcrops. Okay, all right, fair enough. Going back to the scheme for metamorphic rock identification, kind of reviewing it from before, foliated, non-foliated. We talked a lot more about foliated rocks today, okay? But maybe I'll make another video that'll kind of break down and give you some examples so it could be easy to identify metamorphic rocks. So this is Mr. Cloud closing this out today. I hope this was helpful to you, and I hope to see you all soon in class.